let the video start. So, hello. This series, like this playlist that you are currently watching about LISSAJOU's figure, will inform you about different aspects of LISSAJOU's figure. Like, what all things can you infer from those great LISSAJOU's figures? And this is the part 1 of that series. I don't know how long this series will be, because even currently I am learning about LISSAJOU's figures, but the things that I will be sharing will be like something in addition to what books can provide. Like for example, the book that I am currently pursuing is by some author whose name goes by like AP French. I will also show you a glimpse of that book. But yeah, so the thing is, like it has some info which is not like explained in it. So like those are not that difficult to explain either, and therefore I'm able to discuss it here. Still, I will like, it's not like limited to that book, but it is like my view of seeing at least those figures. And yeah, this series will continue. So now let's I hope that you know what is LISSAJOU's figures are. Let me explain them. Well, LISSAJOU's figures are about like what a culmination of two perpendicular SHMs can do. Like for example, you can assume that one SHM happens about the x-axis with one of its extreme at 0, 0, and the other SHM happens at along the y-axis with one of its endpoints, one of its extremes at 0, 0, and then the corresponding sets of y and x trace out a curve which is in most of the cases a closed loop. I mean, most of the cases as in the like the angular frequencies should be commensurable. So what does this commensurable mean? It means that suppose the angular frequency of one of the SMs is like omega 1, and the other one is omega 2, right? So what commensurable means is that you can, in theory, equate them by having some factor multiplied. This factor needs to be a real number. A real number, I say, because yeah, a real number, or you can also say like integers, like positive integers. Yeah, so this is what commensurable means. Also, when they are commensurable, they trace out some closed curve. Like they are not the closed curve that you are imagining, that like they are not like this or this always. They can be of any sort, like they can be like this, they can be like any ziggly wiggly, but they actually form a closed loop. That's what matters with when I say commensurable. And when they are not commensurable, they don't repeat. So in theory, when you extend the time to infinity, they can actually trace they will trace the whole plane, whole part of the plane that they are assigned to. So as in, you can assume that this is the well-known xy coordinate, and this is one of the HM aspect. This is the wait. This is the other SSM aspect. Why is it working? Yeah, and the closed area that they form is the area in which the point will lie, always, because this is in itself this is in itself is an SHM, and this is also an SHM. So in terms of x coordinates, they can at max range from here to here, and in terms of y coordinate, they can at max range from here to here. So in short, they will lie in this rectangle. So when the angular frequency is not commensurable, the point will actually trace the whole part of the plane, like the whole rectangle. The whole region will become black, like if you put a marker on that particle. So the thing that you are seeing on the screen right now are the sets of LISSAJOU's figure. Like they are formed with different ratios of the angular frequencies. Like some of them can be like when the ratios are 1:2, or something can be formed when the ratio is 2:3. But what matters is like the ratio. The actual frequency does not matter. The actual frequency determines how fast they are formed. So let's now move on and see what the book has to offer about our intention. So yeah, this is the book. So for the thing that I have highlighted, right, it says the ratio of the combining frequencies can be found by inspection. It is given by the ratio of the number of tangents made by the figure with the adjacent sides of the rectangle. So what does that mean? Well, what it means is you can go to any figure and say, and just count the number of tangencies and say the two the ratio of the two angular frequencies which led up to this figure. Like in this example, that the middle one, to be specific, it is 1 here, 2 here, then 1, 2, 3. So the ratio of the frequencies that led to this figure is 2:3. Now let's like in the book it's written that you should satisfy yourself of this theoretical justification of this result, and you can check its application to the various curves of figure as shown here. Well, that isn't enough, right? Like we need to understand why that is true. So that's what this video is all about. Well, this video is not scripted, so excuse me if I falter or if I stammer, because stammering is a great problem of mine. Not actually a problem, but still I consider it to be a problem. I know it will go away, but still, let's not deviate too much and get back to it. So there are like wait, oh, I forgot. There are like two ways in which you can go to get to the justification of this fact. One of them is to just go through the path and see how many times uh, like the x component of SHM completes its oscillation when uh, the y component completes one of its oscillations. Like suppose like you can say that the x completes only 1.5 of its oscillations when the other part completes one of its oscillations. So you can say that the frequencies are 2:3 or 3:2. And the second part, which is what I will be doing, is to fix a timing, or fix a point in space in that LISSAJOU's figure, and consider how many times a particular oscillation has occurred. Well, I took my sweet time and drew this pics, not pics, this sketches. I mean, the sketches on the sketches. So the yellow and the orange part of that is tree. That is what I have done you right now, and hope you get them. Like this one is the uh, SSM component of Y. I mean the Y component of the SHM, and this is the X component of the SHM. And those are circular and then bar type. I think that the is just the phasor diagram, and I hope you know what the phasor diagram is. And let me change the color. Yeah. So this one that you're seeing, uh, and let me use the cursor, is like better. So this one that you are seeing right now, the figure on which my cursor is moving, is phasor for y-axis. And as you can see, like I have also drawn the arrows on the LISSAJOU's figure, which show the actual movement of the combinations of this two SHM, the point, the combination which leads to a point, and that moves on this LISSAJOU's figure, and that forms this LISSAJOU's figure, and that's what I have shown here, and the direction in which the point moves actually. So yeah, so initially I have assumed some phase for this one, and I have assumed uh, no phase, I mean no phase for this one. like like it's my convention. Like in books and other stuff you can find that the regular convention in which they have assumed like when the when the I mean the arrow is here, they have assumed that to be the zero phase figure, but I have assumed exactly the opposite one. Also, I have assumed the rotation to be in opposite direction. So now let's start with the explaining part. Like let me draw two lines. And what these lines represent, you will get to know after, I mean, really soon. Draw them nicely straight. Yeah. So this one was like this, if I remember correctly. Yeah, it was right like that only. Yeah. So what does this line represent? Well, this line actually represents the exact movement when the y component is as it was as when it started. So, and for a full rotation, the y component to be same is not all that matters. What we see is phase. So phase is all that matters, and for the two points to be on the same phase, they actually need to be going in the same direction with being at the same position. So as in this on this line, you can see that there are exactly 4 points when the position are kind of same, like here, then here, then here, then here. However, you see that in exactly half of them the direction is actually upward. So here and here the direction is actually upward, and the other two the direction is like downward. So what we get from here is that this point and this point are in phase with respect to the y component. So when we say that we are looking at uh, the number of rotations, the number of oscillations that a particular SSM has undergone, we see the number of times it has reached the same phase. So when we say that the number of rotations that this arrow performs, which corresponds to this omega 1, to be actually how many times it reaches to the same phase, like here or here. So as you can see, that happens exactly twice, right? It starts from here, goes in this curve, returns back here. So that's like one oscillation. Then again it goes like this, return to this point. It's another oscillation. Similarly, when you consider the x coordinate, this being the starting point, you see that there are 3 points when this condition satisfies. I mean the place condition. But we also need to check the direction, and as you can see, everywhere the direction is from left to right. Here also it is, but here it's not like that. Yeah, from left to right, the same one, from left to right. Yeah, here also it is like from left to right. So what it means is, in this point, or in this point, or in this point, the arrow actually moves from here to here. Why? Because here it would be moving towards left, the projection I mean, and here the projection would be moving towards the right. So yeah, so it's like in the ratio of 2 is to 3. So hence we say that the ratio of the frequencies is 2 is to 3. So in this sense, this SHM is kind of sluggish, and this one is like faster or more active, and hence this ratio corresponds to omega 1 is to omega 2. Well, this extrapolation is not only limited to this LISSAJOU's figure. You can do it for any LISSAJOU's figure, and this will work out, trust me, because we have gone through concept, and it's not some kind of funky janky formula which however, if you see, there is also one thing that is written which I have just underlined, is that except in those cases where the LISSAJOU's figure goes into the exact corner of the bounding rectangle, what it means is what we have done is actually applicable uh, to those cases where the figure does not run into the exact corner. I mean, it kind of turns when it reaches the corner, so it's not valid for the cases like I mean, it's not shown here, but let me draw that for you real quick. What it says is like it's not valid when the figure is like this. So obviously you cannot say that this is tangent to this, like the corners are not tangent to anyone, so you cannot say that. But what you can say is like this one is tangent to this side. So why is it so? Let's discuss that right now. However, before starting the next section, what I want to say is that the same LISSAJOU's figure can't be made by two different frequency ratios. So what that means is we can do some sort of magic and extract the information from that figure, that corner like looking figure, to extract some information regarding its frequency ratios. And that's exactly what we are going to do by tweaking the figure. Well, what happens with the general not going towards the extreme corner cases is that they generally go towards one of its edges through one path and then return through another. So there is some kind of separation between those paths, and therefore we are able to see some tangent, like one edge being tangent to the curve. But what happens in this corner type cases is that they go and return in the same path. So that basically happens when this is the phasor diagram for one, this is the phasor diagram for the second one. So this happens exactly when the arrows reach the particular point, like the arrows make the point reach a particular corner at the same time. So when this happens, what this arrow says is that the point needs to go in this direction, and what this arrow says is that the point needs to go in this direction. So they return back, and exactly opposite of this happens when the point actually moves to this direction. And that situation can actually be negated if we somehow kind of like as I said, um, tweak the figure to display two different paths. So what I mean by that is, like, what happens in reality is that it goes in this direction and then returns back like this. What I'm saying is that we can actually uh, shift the returning back path a little down. I mean, in theory, actually, that way we will form something like this. It goes outside, but I mean, just for the sake, just assume that uh, this is also the corner. Yeah. So and now, I mean, this is all. Just assume that this is also the edge, and this is also the edge. Just assumption. I know it's like not visible right now, but just assume that, okay, and then connect them smoothly. Now the magic happens. Now what you see is it touches this edge once, so it's like one over here, and it touches this edge twice, so it is two over here, which satisfies this relation. Let us do for some other figure, like for example this one. We smoothly converge it with the displaced line. What we get is 1 is to 1. Let me take another example. This one is what we already did, so I will go with this one. Yeah, so displace a bit down and then do the exact same curve. Oops, it went down. Yeah, and then join them. Now what you see is 1 2 3. Oh, oopsie daisy. 3 and 1 over here. So it should be, in theory, in practical, in theory, I don't know, in practical, like in practical and in theory, 1 is to 3. Let's see if that is the case. Yeah, that is the case. Yeah, you can do that for every corner type curve that I see in the figure. The next question that arises due to just mere consequence is that why should that be true? No, why should what I did earlier is true? I mean, the like shifting the figure into two parts, then joining them through smooth curves and doing some such fancy steps. Why did it work? Let us explain that. So when we count the number of tangency points, what we are actually counting is the number of times the point has actually come towards the edge or has gone away from the edge. Either but not both. Okay, so when we say it has three tangency points, we actually mean that there are like three cases where the point actually comes towards the edge and actually reaches there. Like the red ones represent that, and the orange one represents the number of times when the point actually recedes away after reaching near the edge. Therefore, when we it's not there here. It's here. Yeah, I mean not here also. It's kind of like here. Yeah. So when we like shift the figure downwards and do such fancy steps, what we actually did is we introduced a little uh, tendency point over here and over here. For now, we have two uh, tangency points where we can say that the point comes closer to the edge and then recedes away, like here and here. Similarly, we have two of such cases in this edge and one such case in this edge, which leads to this so-called 1:2 angular frequency ratio. So yeah, I think this was what uh, the part 1 of LISSAJOU's figure, which only like explains this much part of the whole paragraph has to offer. See you in the next video. Bye.